So subatomic particles. We talked about, atoms are the building blocks of matter. Atoms actually do have some smaller inside working parts, and those are called subatomic, meaning smaller than atom particles. And all atoms are composed of the same kinds of subatomic particles. And the three most important ones are protons, neutrons. Man, I don't know. This program hates me this year. Neutrons and electrons. And we need to have a rough understanding of what these particles are. So protons and neutrons have essentially the same mass. We think of them as being the same size. They're both like crazy small. So proton, 1.67262 times 10 to the minus 27 kilograms. We're almost never going to use that actual number. The mass of a neutron, almost exactly the same. It differs in the fourth significant figure, so it just really doesn't matter, the difference. Both of them crazy small. An electron, also really small, a lot smaller though. This is 10 to the minus 27, 10 to the minus 31. So electrons are close to 2,000 times less massive than protons and neutrons. And here's an analogy to help us understand the relationship there. So if the proton had the mass of a baseball, then an electron would have the mass of a rice grain. So really, really tiny. Well, kilogram is not a great unit for measuring something so small because we end up with these really, really small numbers. So we make up another unit that's more useful in size. And that sounds a little flippant that, oh, we just created a unit. Guess what? All of the units were just made up at some point, right? So it's really not that crazy. So this one has a very creative name. But it is very descriptive. Atomic mass unit. So it's a mass unit for measuring the size of atoms. And the abbreviation is AMU, and you would read that as AMU, not AMU, some strange relative of an emu. Okay, so what is an AMU? An AMU is defined as 1/12 the mass of a carbon atom that contains 6 protons and 6 neutrons. So because of that definition, the mass of a proton or the mass of a neutron is very close to 1 atomic mass unit. So that's convenient. Because a carbon atom with 6 protons and 6 neutrons would have a total of 12 of these relatively massive particles. And that would weigh 1/12, or it would weigh 12 atomic mass units. Some of these particles are charged. The proton has a charge and the electron has a charge. And we can measure their charges in coulombs. Proton is plus 1.60218 times 10 to the minus 19 coulombs. An electron, same crazy number, opposite in sign. In chemistry, we really don't need that actual number. What we need are the relative charges, easier to remember, +1 and -1. So the proton starts with a P, and it's positive, which also starts with a P. Don't play with that. Oh, okay. Is it hissing? Yeah. Okay, hang on. So protons are positive. The neutron is neutral, just like the beginning of its name suggests. Neutral, so it has 0 charge. The electron is the other one. It's negative. So it has a -1 charge. So we need to know, this part, the charges. You do not need to know these numbers. Occasionally, you might need that number. We just look it up. I don't know what those are off the top of my head. Here are the actual masses. You might need one of those for a homework problem. But again, you don't memorize those. Oh, I didn't do this very well. Let's try that again. So we want to know these. And atomic mass units, so that's approximately 1. This is approximately 1. And that's approximately 0. And so I want you to know those those masses. 1, 1, and 0, plus 1, 0, and minus 1. Okay, proton, neutron, and electron. So matter is usually charge neutral, meaning it doesn't have an overall positive or negative charge because you have an equal number of protons and electrons, and they have opposite charges, so their charges add up to 0. When we do have a net charge, things become very unstable, and they will become neutrally charged in very dramatic ways. That's one of the things that happens in an electrical storm where you have the lightning. Lightning is caused by a charge imbalance in matter between what's up in the clouds and what's down on the ground. Another example of that is static electric shocks. So in the winter, you're shuffling around the house on the carpet in your socks, and then you touch something metal, right? And you get this little shock. It's because you built up a charge, and when you touch that metal object, which is grounded, then the charge equalizes. So elements are defined by how many protons they have. I kind of think as the number of protons as sort of being like the personality or the soul of the atom. So number of protons defines the element. We call that the atomic number. It's given the symbol Z. You might think, well, it should be A, but it's Z. And it's because it comes from the German word meaning number. So here is a helium balloon. All helium atoms have 2 protons. That is what defines it as being a helium atom. The lead in your pencil is made out of carbon. Every carbon atom has 6 protons. Every single one, 6 protons. If it has a different number of protons, it's a different element. So on the periodic table, we have the element names and symbols. Well, this table has the names. Most of them do not because it takes up a lot of space. So here's sodium. Here's its element symbol, which is one of the things you're supposed to memorize. And then there's this integer number above it, 11. That's the atomic number. So all of the elements on here, we can tell by looking at the periodic table how many protons they have. So if we look at, say, bismuth down here, bismuth has 83 protons. And they are arranged in this table in order of increasing atomic number. So we define each element using a unique symbol. The symbols have 1 or 2 letters. The first letter is always capitalized. The second letter, if there is one, is never capitalized. So each element has a unique atomic number and a unique symbol. And we have to be precise in this, or we would have to write everything out, and that would just be super tedious. So we've got helium. The chemical symbol is capital H, lowercase e. Carbon is capital C. Many of the element symbols are the first letter or the first 2 letters of the element's name. But some of them, some of the symbols come from their Latin names. And so those are the ones that don't seem to make any sense. Like, how do you get Na from the word sodium? There's no N and there's no A in sodium. Well, that's because it's not based on the English name. It's based on the Latin name natrium. So it's the first 2 letters of the Latin name. So some of these are going to make sense. Some of them are not going to make much sense. And that's why you have to memorize them. Yes?
Do you think it would help if we learned the Latin for some?
For some of them, if you learn the Latin name, it might help you make sense of it, yeah.
Okay.
But I'm not going to quiz you on the Latin names.
Yeah.
Some of them are a real mouthful. So all atoms of a given element have the same number of protons. They do not necessarily have the same number of neutrons. Okay? So if you have atoms that have the same number of protons but different numbers of neutrons, they are the same element, but they're not exactly the same as each other. And so we call those isotopes. Iso is a prefix that means the same. I'm not sure what tope means. honestly. But iso means the same. So all neon atoms have 10 protons, but some of them have 10 neutrons, some have 11 neutrons, some have 12 neutrons. That information is not on the periodic table. Because protons and neutrons are the particles that contribute to the mass of the atom, these isotopes are not going to have the same mass as each other, even though they are the same element. So any given element may have only one isotope, or it could have 2 or 3 or more isotopes. The relative abundance of each of those isotopes is relatively constant no matter where you find the element. We call that the natural abundance, and it's usually expressed as a percentage. So the natural abundance of an element, of an isotope. So we need a way to identify the different isotopes of an element, and so we use the mass number. The mass number has the symbol A. I would have made that the atomic number, but they didn't ask me. Partly because I wasn't even born yet, you know. So the mass number is A. The mass number is the number of massive particles. So it's the number of protons plus the number of neutrons in that given isotope. So we can symbolize different isotopes in a couple of ways. One is a nuclear symbol. So here capital X represents the chemical symbol for the element. Example down here would be neon, so Ne. And then the mass number is a superscript on the left, and the atomic number, the number of protons, is a subscript on the left. So 3 isotopes of neon are shown here. The mass numbers are different, 20, 21, and 22, but the atomic numbers are all the same, because in order to be neon, you have to have 10 protons. So if you need to know how many neutrons these guys are, they're not neutrons, how many they have, you can just do some subtraction here. 20 minus 10 is 10. So this one has 10 neutrons, this one has 11 neutrons, this one has 12 neutrons. So that information is just kind of hiding in there. Another way to specify them is to use either the element symbol or the element name, a dash, and the mass number. Because do we really need to remind ourselves that neon has 11 protons? No, because it's on the periodic table. And no chemist is ever without a periodic table. I have the periodic table app on my phone, so anytime I want to know how many protons neon has, I'm good. You just never know when you might want that information. It's the mass number that we use to specify the different isotopes. If you want to know the neutrons, you just subtract the number of protons. So neon 20, neon 21, neon 22. Those are the 3 different isotopes for neon. So here's just a table showing the different information that we get about these 3 isotopes for neon. So the symbol, we could represent it this way, or we can do it in this nuclear symbol method. This is really tricky to do on a computer because you have to go into a math editor and do the stacked superscript, subscript thing. It's a real pain. So Ne20 is a lot simpler. Number of protons, they all have the same number of protons. Number of neutrons, we can get this from this mass number by subtracting the number of protons. The mass number is the total of protons plus neutrons. Okay? Now, the natural abundances over here, 90.48% of neon is neon 20. 0.27% is neon 21, and 9.25% is neon 22. Why is it those particular numbers? Because it is. We have studied neon and measured it and stuff, and those are the natural abundances. This is also not something you would memorize. You would not memorize how many isotopes a given element has. That's not something that regular people keep in their heads. There are, I'm sure, people who know that, but I don't know those people. So what should we be able to do? we should be able to answer questions like this. What are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? You need a periodic table to answer these questions. So the atomic number, that's the number of protons. We read that straight off the periodic table. So we're talking about carbon, so we find carbon on the periodic table. The number above the C is 6. That is the atomic number. So the atomic number, symbolized with a capital Z, the atomic number is 6. So it's 6 protons. The mass number, oh, you got a question?
No.
The mass number is not listed on the periodic table because the mass number is going to be different for each isotope. And those aren't shown on the periodic table. That's why they're telling us there's 7 neutrons. The mass number, A, is number of protons plus neutrons. So we find from the periodic table 6 protons, and we add 7 because the question, can you get that? The question tells us there's 7 neutrons. So 6 plus 7, last I checked, was 13. So that's the mass number. Now the symbol, it doesn't specify which kind of symbol. You should be able to do both kinds. So you could say this is C-13. The element symbol, dash, and the mass number. Or the fancier one, we've got the element symbol, we've got the mass number on top, and we've got the atomic number on the bottom. And the way I remember which one goes on top is it's stacked up so you could subtract and find the number of neutrons. I'm sure that's not why they did it, but it's useful. So any questions about that one?
Doesn't matter if the atomic number is big or small, you have to write it in the bottom?
Yes, the atomic number always goes on the bottom. And the atomic number cannot be smaller than the mass number because that would mean you'd have negative neutrons, right? So it is possible for the mass number and the atomic number to be the same, but that doesn't happen very often. So how many protons and neutrons are present in an atom of this? Well, the number of protons is given by that bottom number, right? So we can look at the symbol, or we could find potassium on the periodic table, and there's the 19. So 19 protons, and how many neutrons? 20, yeah, 39 minus 19. So the mass number minus the number of protons gives us the number of neutrons. The number of neutrons is often in the ballpark of the number of protons, but there's really no way to predict it from the periodic table. Any questions? So what about the electrons? If we have a neutral atom, and all atoms are neutral, then the number of protons and the number of electrons has to be equal, because those are the charged particles, and atoms are neutral in charge. So we can also find out how many electrons an atom has by looking at the periodic table. It's the same as the atomic number. But the number of electrons can change. So I think of as the protons as being like the personality or the soul of the atom. I think of the electrons as being a little bit like its clothing or its outward appearance, the color of its hair, or what kind of a jacket it's wearing. The electrons are on the outside, the protons are in the nucleus on the inside. Number of electrons can change. If you change the number of electrons, now we're going to have a charge on the ion. And the charge will depend on the difference between the number of protons and electrons. So we can have positively charged ions. Na plus. This plus sign here means that it has a positive 1 charge. So it has 1 more proton than it does electrons. You can't change the number of protons, it's the number of electrons that change. Positively charged ions are called cat ions. If you like cats, this works. I have positive feelings for cats. Cations are positive. If you don't like cats, well, anions are the negative ones. They both end with ion, right? So there's an N in both of them. But anion has an extra N, and anions are negative. F minus is an anion. It has a negative charge because it's gained an electron. Any questions? And they aren't cations and anions, they're cations and anions.